All right. Hello, everyone, and welcome to Cultivating Learning, using rockets to investigate forces in motion. We are so excited to have you all here with us today. In this session, we're going to explore curricular connections between space exploration, forces, and motion. Together, we're going to dive into a variety of ways to use rocketry in the classroom, from digital tools to hands-on activities, all for a range of grade and skill levels. You'll leave to get with ready-to-use activities and suggestions for scalability. So we're going to be doing a lot together today. My name is Tess, and I'm an educator at the Smithsonian Office for Educational Technology, and I'm joined today by two fantastic guests from the National Air and Space Museum. They are Shannon Baldioli, the Educator Engagement Specialist, and Kelsey Vollmer, a fellow at the museum. They are going to be doing the bulk of today's session. They are expert educators who are going to walk us through all these ideas for using rocketry in the classroom. As we go throughout today's session, this is going to be interactive, and we want to hear questions, ideas, and more from you. We'll be talking a little bit later on how to use the chat if this is your first time joining a Cultivating Learning session, but don't hold back. We want to hear from you. And part of the modeling activities we're going to be doing today, we want to hear from you, especially during those. As we model activities today, you may have noticed in the session description that we're going to be modeling one that uses materials that you will likely find at home. So if you'd like to build a straw rocket, that's going to be our activity today. During the session with us, you'll want to locate the following: drinking straws. I have a reusable one, paper, Post-its work really well, tape, and other things to add decoration and dimension. So you might bring stickers, paper clips, markers, and more. At the end of today's session, as we go through all of this, we'll also have some time for Q&A. So if we don't get to your question during kind of the run of the main session, don't worry. We'll have some time for larger questions at the end. And that's a great time to ask about, say, if you're curious about specific resources from the museum, ideas from Shannon and Kelsey on how you might bring this into your specific classroom environment, and more. So some of the digital resources we'll be sharing today are located on the Smithsonian Learning Lab, which is a free website where you can discover, create, and share with digital museum resources from across the Smithsonian. Specifically for today's session, we've built a Learning Lab collection that walks through how to build the straw rocket that we'll be building together. So you'll have photos and instructions. It also links to some other resources that you can bring into your classroom to explore this idea of rocketry, forces, and motion. So we won't be going into an in-depth tutorial on how to use the Learning Lab to find resources like the ones we're going to share and create learning experiences like the ones we'll be talking about. But if you're interested in learning more, you can do so at our Help Center. The URL is here at the bottom of the screen. Here you'll find step-by-step instructions on how to do everything on the lab. You'll also find tutorial videos and videos like this one, where we invite educators to share some of their favorite ways to teach with museum objects. So this is a great time to mention today's session will be archived. So if you need to leave a little bit early, you want to share this with a colleague, you want to come back later, you can. The recorded session will be made available right after the session ends at the location you're watching it now, whether you are joining us on YouTube or Facebook. So again, this session is interactive and we want to hear your ideas and questions. So if you're joining us on YouTube, you can use the chat to share thoughts and ideas with us. You'll find it to the right of the video. And if you're joining us on Facebook, you can use the comment box to send ideas and questions to us. With that, we would love to hear who's joining us today. We would love to learn a little bit more about you. So take a moment to share where you're joining us from and what you teach. We would love to hear. And hopefully with that information, we can better tie this session to meet your needs. So I'll give you a moment to do that. And perhaps while we wait for those ideas to come in, Kelsey and Shannon, I can turn it over to you.
Awesome. Thank you, Tess. We are really excited to be here to talk to you about rocketry today and using rocketry in the classroom. So, as Tess said, I am the Educator Engagement Specialist at the National Air and Space Museum. I am the coordinator of most of our professional development efforts at the museum. One of those efforts is the Teacher Innovator Institute, which is a national professional development program. And that's how I met Kelsey. She was a participant in TII, the Institute, way back in our first year in 2018. And then as part of her role as an alumna of TII, she's joined me for a year here in DC as a fellow. And I'll let her tell you a little bit about where she came from.
Sure, thanks, Shannon. So as Shannon said, I get to spend 13 months in DC working with the National Air and Space Museum and the Teacher Innovator Institute. And Shannon, I'm noticing that we have some teacher innovators in the chat coming from Cincinnati and Oklahoma, so that's really exciting. I came from Seattle, Washington, where I taught K through 5 science labs. So I have taught anything from high school biology to teaching at an informal institution, botanical garden, and have most recently been in the classroom K through 5 working with the science curriculum there. So I use rockets with our fifth graders and build in some different rocket activities with all the grades. So I have quite a bit of experience doing this in the classroom.
So we're going to talk today about lots of different ways that you can use rocketry, whether you've never done it before or you are sort of an expert in rocketry. So we wanted to get started taking your temperature on rockets. So on a scale of Redstone to Saturn V, Redstone being the little bitty rocket on the left side of the chart there, and Saturn V being the big beefy one on the right that took our astronauts to the moon. How comfortable are you using rocketry with students? So you could use numbers 1 through 5, 1 being the least comfortable, 5 being the most. Or if you were a rocket fan and you could use Redstone, you could use Titan, or Saturn 1, Saturn 5. So let us know how comfortable you are using rocketry in the classroom.
All right, Shannon, I'm seeing an Atlas and a Titan so far.
Perfect. I'm not scrolled down far enough.
Oh, we got a Redstone.
Awesome.
Another Atlas has come in.
So it seems like 1.5. Okay. Right between those two programs. We're not quite suborbital, but not quite in orbit yet. Got it. Awesome. So it seems like a lot of folks are just sort of dipping their feet in, maybe a couple of experts or folks that are more comfortable. So as I said, we are going to be exploring different rocketry techniques and activities to explore force and motion. So any of you who are using the next gen science standards will know that, especially in late elementary and middle school, there's lots of different force and motion standards. So there's a lot of Newton's laws in there that you're talking to students about changing an object's motion by applying a force, using observations, measurements, and then also in third grade, I think we're talking about providing some evidence of force and motion. So we're going to touch on those different things as we go with each of these different activities, and would love for you to continue talking with each other in the chat if you've got some curricular connections as well. So one thing we wanted to introduce before we dive into activities is an awesome online resource from the National Air and Space Museum. Not a ton of people know about it, but when you learn about it, I think a lot of teachers really love it and use it a ton. Kelsey's going to talk in just a moment about how she uses it in her classroom. But How Things Fly is actually a brick and mortar exhibition at the National Air and Space Museum's flagship building on the National Mall. It has been in existence since the mid-90s. And the exhibition is one of our most hands-on exhibits. It talks about the different forces of flight, gravity and air, structures and materials. It's currently undergoing renovation, as is most of the rest of the museum, but in a couple of years it will open up brand new with renewed design space and exhibitions that you can interact with. And the How Things Fly website will remain up in perpetuity as the sort of online version to that brick and mortar exhibition. And the website sort of digs into some of those STEM concepts behind how things fly. So there's great videos, other activities as well. And Kelsey actually uses How Things Fly in the classroom quite often. So I'm going to drive the website while she tells you about a few things that she really likes about it.
Thanks, Shannon. I think one of the really great things that I love about How Things Fly, so not only with the physical exhibit itself at the museum, it's such an interactive, hands-on exhibit, which is a little different than many of our other exhibits, but it allows the visitors to really feel the forces of flight and feel the aerodynamics that go into play here. And the website does a great job with their interactives, getting students involved in this as well. So I use it to find resources of things that I can teach. So I know that there's some really great little bits of information with the Ask an Explainer that we see there. They also have really great resources for teaching things like Bernoulli's principle with students, or propellers, and they give you some activity guides to go with those. And then I also like to send students to the website and let them explore. And so when talking about something like rocketry, or really this bridge between flight and rocketry, I like to send them to the propulsion page. So propulsion is talking about how we get that thrust, and sometimes, well, in airplanes, we can do that in a number of ways, whether that be propellers all the way to jet engines, and then that bridge to rocket propulsion and actually using fuel to provide the thrust has a lot of really great ways of photos and descriptions for students to interact with. So here you can see a comparison to a balloon. And when I have a balloon full of air and I'm holding it, all of the force on the inside of the balloon and the outside of the balloon is equal. And then when I let go of that, that air is going to rush out, because no longer do I have those equal forces. I have an imbalanced force. And with the air rushing out, I'm going to get that action reaction that we talk about with laws of motion. And that is very similar to a rocket and a rocket engine providing propulsion and thrust, which then moves the rocket into, moves it up away from the ground, right? So you have an action reaction happening there. And one of my favorite things that the students get to do, if you keep going down, Shannon, I'm hoping it's down there. Oh yes, the Rocket Lab. Rocket Lab is one of these fun interactive pieces where you can go into, if you click on test your design skills, students will be able to build a simulated rocket and then launch it and see, does it work? Did it not work? And get some suggestions for design elements. So they get a budget that they're working with, they get a task that they're working with. So sometimes it's carrying lots of cargo to outer space. Sometimes it's taking a satellite up, and they have to think about that and build their rocket design to those specifications, if you will. So it kind of puts them in the chair of a NASA engineer, thinking about not only the purpose of the rocket, but also the budget behind it. So How Things Fly, I recommend it to anybody I talk to who teaches flight and rocketry. It's such a wonderful website, and it continues to get better. Shannon and I were just talking about how they've added lots of really great things to it. So always go back and check.
And another thing I really love about How Things Fly, and you can see them in the middle of the page here, are some of these animations. Just really great, simple animations that show some of the forces that are at play, or show how a jet or piston engine work, which can be really complicated when you're just trying to sort of talk through them with students. So can't recommend it enough. Visit howthingsfly.si.edu. That's also in the link package that was shared in the session description too. So we're going to talk about a variety of different activities today that you can do with rocketry. And I've placed them on this sort of chart here to kind of give folks an idea as we talk about them, that we're working our way through some different pieces here. So I've categorized them as low prep to high prep. So low prep, we're talking about less than an hour. You could do these really quickly. One of those activities we're going to do together in just a few minutes. And then high prep often takes several class periods and requires some more materials, maybe some more specialized things that you need. And then low tech to high tech, I think most people will get what I mean there, but from, just things like we're going to use in a couple minutes, like straws and Post-its that you can grab out of a drawer in your home, or Play-Doh that you can grab out of your 4-year-old's bin in the basement, to things that are much more specialized that you would have to purchase, like 3D printers or model rocket kits. So we're going to talk about all of these different activities today. We'd love to hear in the chat if folks are using these different things or other rocketry resources that you use. So the first thing we're going to talk about is straw rockets, and we want to invite everyone, if you'd like to make one with us, we can do so. So all you need to have is a straw. I have this metal drinking straw, and paper are sort of our two main components here. Post-its work really great because you've got that little sticky edge that can kind of hold it in place. But we're going to sort of make them together here and talk through it a little bit. You can see on the slide there that I've laid these all out to talk about approximate cost. I'm approximating all of them, so it could be that it costs next to nothing. It could be that it costs a little bit more where you are. Prep time, again, is an estimate, but usually a pretty good one. Tech, and then those key concepts, right? So with all rockets, we're often talking about weight and balance, and we're talking about projectile motion. So I've got my straw and my Post-it. I'm just going to take my Post-it and start wrapping it around the straw. Kelsey and I were practicing this early, and it's a little bit of a tricky balance to find. You want it to be wrapped pretty tightly around the straw, but you also don't want it to be wrapped so tight that it can't move along the straw. So it's going to come hopefully shooting off of one end when we get finished. So I'm wrapping it around so it's got like just a little bit of breathing room there. And once I have it wrapped around, I'm going to grab a piece of tape. I've got some Scotch tape because my daughter told me I couldn't use her washi tape. That's for special occasions. I know.
Shannon, I've got some washi tape, so I'm going to use mine just since you can't use yours.
Well, I can't use llama washi tape because shout out to Stella. She was using it when I wanted it. And then I'm just going to take it and wrap it so it's tight around my straw. And then the easiest thing to do is to just take the Post-it that's on top of the straw and kind of crimp it and fold it over so you've sealed it. We were also talking about this before. I think most everyone has in life created a straw rocket, maybe when you're sitting across from your mom at IHOP and you take a little piece of the straw off but leave a tiny bit of that paper wrapper on the plastic straw. And then you might try and shoot the paper wrapper off of the end of the straw. Another shout out to my family. This happened once, and the straw went right up my brother's nose. So it was a perfect shot, and it's a sort of memorable holiday thing that we talk about. But so I've got my own version of that IHOP straw here with the top of the Post-it folded over. So it should be able to come right off of the straw. I'm going to attempt to launch it off of the end of this straw, and we'll see if it sort of blows past the camera here. Oh, there it went across my bedroom somewhere. Hopefully not into a potted plant, but I have backups. So you can have students do this and experiment, this really simple experiment with how far the paper rocket will fly. How does it fly, right? This is a great way to start introducing projectile motion and talking about gravity, right? Things don't keep going on forever. They go in that arc that, right? Isaac Newton talked about that cannon. If you could shoot a cannon off of the side of the earth, things would drop in an arc unless you could shoot it so hard and so far that things kept falling around the earth, which is what happens with things like the International Space Station, right? It's falling around the earth. That's why astronauts are in free fall. So you could have students do this with your straw. You could, like in the image there on screen, like Kelsey did, actually draw a rocket on there. And then if you wanted to level it up a little bit, you can also add some weight and dimension and have students explore exactly how things change when you do that. So I have some unfortunately dried out Play-Doh here, and I can put that on the end of my straw rocket and see if that changes it by adding some weight. You could also, if you were using slightly better materials than I am right now, than dried out modeling clay, you could make it into an actual nose cone shape and explore with students the idea of why rocket nose cones are shaped that way. Is there a reason that rockets are sort of pointy? And there's lots of great ways to go with that. You could talk about sort of the mimicking the animal world, other places that we use things like aerodynamics. So let's see if my Play-Doh rocket flies too. Oh, that one flew almost nowhere. It just landed on my keyboard because it's a little too heavy. Great exploration there. You can add shape, you could add fins. I'm not going to do it right now, so we can go on to the next activity in a moment. But pipe cleaners are a great way to add fins really easily because you can bend them up. I also have these wiki sticks. If you've never used wiki sticks, they're kind of like a candle wick. They're wrapped in like a waxy material, and they can be bent and used. They're really fun to practice letters with your kids if you wanted to do that, or put them on an airplane window, which is how we use them to entertain on trips too. Kelsey, how's your rocket looking?
Well, I leveled up and I put an LED on the end of mine.
All right.
Problem with this is the battery makes it kind of heavy, but you can also integrate some art into your straw rocket. It still flew pretty good. Luckily, that light bulb is pretty aerodynamic. And Shannon, I really liked how you talked about getting inspired from nature. We call that biomimicry whenever humans take design elements from nature. Nature has been designing itself to be the most efficient thing for millions of years. And so I think humans have a lot to learn. And one of my favorite examples of biomimicry is the bullet trains in Japan, and how when they first designed them, they were super loud. They would go into these tunnels and they would cause the air to really bunch up on itself and release a boom whenever the train came out. And then an engineer who happened to be an avid bird watcher was like, well, the kingfisher is able to dive into water with no effect at all. And so they redesigned the front of the bullet train, and it's now a super quiet, super efficient train. So similar to rockets, right? Rockets kind of get that shape for aerodynamics, which comes from nature.
That's amazing. I had never heard that before.
Oh, yeah.
One of my favorite biomimicry pieces is some wind turbines have textured edges based on whale fins because they move so sleekly through the water. And if folks are experimenting with these at home, I know it came up in the comments, but please feel free to share in the chat your experiments and your wonderings and successes that you're having with your straw rockets. While we continue to talk about straw rockets, but in a slightly different way. So now we're moving up the sort of tech ladder here and leveling up with an actual straw rocket launcher. So the ones here are made by Pittsco, but you can make them yourself. You can make them out of PVC. I think in our link package in our learning lab, we've provided some other options as well. But leveling this up with cost and time, right, for a couple $100, Pittsco makes these launchers that are either very small or these tall ones that you lift up to a certain space and then drop it, and it pushes air through the little launcher and launches your rockets. These are really fun to do with students. If you roll out a long roll of butcher paper, and you could put a little bit of Sharpie marker on the end, or if you want to add a little bit of art to it too, we have a teacher in TII that actually created a really big, I think, retirement card for his principal. And the students all put cotton balls with paint on the end of the rockets and shot them at the card. So there was some steam in there too. But this is great because there's you can change the angle of launch, and students can really start to explore and see the differences when you change that angle of launch, or when you lift the launcher up a little bit higher and use more force to drop it if the rocket goes further or not as far. And I think what often happens is students find that there's sort of a sweet balance there. Like, you're not just going to lift it up and slam it down. That doesn't work quite as well as if you have some finesse. So you can talk about launch angle and weight and balance. You can talk a bit about stability. And then, of course, there's that steam piece in there if you wanted to add some paint or something like that.
Well, and I know, Shannon, there's some really great connections you can make with NASA missions as well. I know some teachers who developed a lesson with straw rockets to talk about the DART mission, which was basically a mission to send a projectile towards an asteroid to see if we can make it move. Asteroid? Comet? No, asteroid. And so you could give students a specific target, and somebody said that in the chat, like having a very specific target. So it's not necessarily that you're trying to get it to go the farthest, because that's what a lot of students want to do. They just want to make the straw rocket go as far as possible, but really give them that design challenge of, hey, we want you to hit this exact spot, and the person or the group that gets closest is going to be the success in the succeeders in that case. Somebody asked about a smoothie straw working better than a standard straw. That's so interesting. I think you should do that with students and see. I know that if you are just doing it with your breath, a smoothie straw would work. I know with the straw rocket launchers, they do have a specific diameter of straw that you have to use. So while you think, oh, having these giant smoothie straws might be really cool, they wouldn't work on the specific rocket launchers that Pittsco sells, but you could always build your own, or have students design and see what works best for them.
And the smoothie straw, one of the things I think is really important with the straw rockets is just how tight you wrap it. And that's a variable that students will explore. That Les Kelsey and I were prepping. That's something that we were exploring. I wrapped my first one not quite tight enough. And what I ended up doing was blowing in the straw. And then my breath just kept coming back to me around the edges of the rocket. So that's a sort of fun experiment to do with students too, that finesse of wrapping it up there.
And then Diane also added a comment about using a small straw inside of the big straw. So you're instead of putting your Post-it note and wrapping the paper around, you would have that more sturdy structure of a smoothie straw, and then you could build your fins and your nose cone on top of that. That's a great idea.
I love that. Straw within a straw inception. So now we're leveling up the prep again, and we're moving to something definitely messier, but something that students think is like absolutely amazing, right? Many people have done Alka-Seltzer rockets or baking soda and vinegar rockets. So this is like a tiny little dip into chemical rockets. I know film canisters aren't as easy to come by these days. You generally have to buy them from a specialty, like science distributor often has them.
You can buy them from Amazon, Shannon.
Oh, okay, perfect. Well, so you can get them, but they're not as like ubiquitous as they would have been a few years ago when I could have just gone rummaging through my dad's extensive camera film collection. So basically all you need is film canisters or small closable containers that aren't like a screw top, because you need them to be able to pop off as that reaction is happening. And then Alka-Seltzer, which you can purchase in those little individual packs. And you're exploring those same concepts, right? So basically what happens is you take your Alka-Seltzer tab, or you take your water or vinegar, if you're doing the vinegar and baking soda, toss it into the container, quick drop the Alka-Seltzer tablet in, and then put the lid on and turn it over so that in a few seconds, your rocket goes kind of like up into the air. One of the really great variables you can experiment with students is the amount of Alka-Seltzer that goes in. Although I've been told that some students, you break it into fourths or whatever, but kids are just so excited to do this. They may not necessarily be remembering if they put a tablet in there, if they put the whole tablet in there. But this is also a great place that you can, as you're exploring rocketry, introduce chemical reactions and sort of what's happening inside of a rocket. By moving on to using actual chemicals rather than air. So I'm also seeing some great comments still on the straw rockets about too much clay can be a real problem. That was my problem just a few minutes ago when it flopped on my keyboard, and different kinds of Post-it notes. Adore that. And I think it's time for a steam break.
Steam break! Oh my gosh, I got really excited when we got to the Alka-Seltzer page because I knew what was coming. So just like Shannon was talking about with chemical reactions, I actually, not only do I use Alka-Seltzer rockets with my 5th grade students whenever we are into our rocketry unit and talking about that idea of chemical reactions and providing the thrust, which makes the thing go up. And they a lot of times will design cones. They'll actually add to the film canister itself. So they'll add paper to make it longer, add the shape of the cones, the fins. But in 2nd grade, so if I have any elementary teachers out there or middle school who are talking about chemical reactions, solids, liquids, gases, I love to use Alka-Seltzer and paint to really show that we can go from a solid, combine it with a liquid, and based on the properties of those things, when they react, they create a gas, and gas takes up space because it's matter, and it grows and grows and grows until the pressure builds, and you pop the top of your film canister. And so this takes a little bit of experimenting, depending on the type of paint you have, depending on a lot of variables. I just mix the paint with a little bit of water. And that's the part that you kind of have to do some chemistry on to really find your good balance. But mix the paint with a little bit of water. We put the Alka-Seltzer in the film canister. The hardest part for this one, especially with littles, is like getting that lid snapped on without being too afraid that paint's going to pop in their face. But luckily with the paint, it takes a little bit longer for the chemical reaction to happen. So you have a little bit more time. But they snap the lid on, turn it upside down. And I've done anything from each student gets an individual little, I just cut up some poster board that they did it on, and then we hung those up in the classroom. I've also had them, this is my wonder sign that I cut out the letters with a laser cutter and then painted them white. And when we did this experiment with students, they helped me decorate my classroom. So that was tons of fun as well. So always wonderful to bring art into science. I have never had a bad experience when I bring that art piece in. It usually brings a lot of students' interest who may think that they are not interested in science, but they might be really interested in art. It really invests them in what you're teaching. So I'm a huge proponent of making STEM into STEAM. And if you have any questions about other ideas, let me know.
And this is a cool one too. Kelsey touched on it a little bit, but different color paint sometimes has like a slightly different reaction. So it takes a little longer for some colors or not other colors. I know in a previous life at a different institution, we created paint that was safe to put in your mouth for various reasons. And you can do that by crushing up chalk and mixing it with water. And Kelsey and I were wondering together yesterday whether that's actually something that could work in this or if it would change the chemical reaction. So this is also a chemistry rabbit hole you could dive down independent of rocketry, which is a really fun one too. So if anyone experiments with it, please let us know if the chalk paint works too.
You know, Shannon, this is reminding me, and some of our comments too, Cheryl said it would be really interesting to test, or maybe it sounds like Cheryl has done this, testing hot water versus cold water as well. And you can get timing of chemical reactions. So depending on the age of your student and how much time you have to teach this, you could really dive into it or let students decide, what do they want to test, right? So maybe they want to test, does the size of the Alka-Seltzer tablet change the reaction time, or does the hot water versus cold water change the reaction time? So endless possibilities with these experiments.
Love it. So then leveling this one up a little bit, you can do water-powered rockets. So there's endless possibilities with this sort of kind of a simple, from an Alka-Seltzer rocket to like a water rocket where you use something like a bicycle pump to pump it up, and then you can shoot it into the air based on that water pressure. But to level that up, you can, if you have access to 3D printing, have students create or just explore and print fins and nose cones for their rockets. So fins and nose cones are the reasons that we can get rockets to the moon, those propulsion systems and sophisticated engines, the way they move. But these propulsion systems wouldn't be able to get us places if we weren't able to control them, right? Kelsey we talked about biomimicry and sort of the shape of the top of a rocket. But fins are also really important for control so that rockets go where we want them to go. And having students explore that is great. So you can see in the images there, these are images from Tinkercad, there's Tinkercad and Thingiverse, which are software programs that you can use to either build 3D prints yourself, or depending on the Creative Commons licensing, you can use the 3D prints that other people have created. So these actually are ones that you can go on and print these nose cones for specific types of rockets. And then the image at the top, they're made to go around a 1 or 2 liter bottle and create fins for a bottle rocket. So they just kind of slide on there, which is really cool. So depending on, I know a lot of libraries, media centers, and schools often have a 3D printer. Sometimes we have STEAM labs. 3D printers can be costly. You can get them, for not a huge expense, but depending on your access to a 3D printer, this doesn't have to be a super expensive level up. But you can have students create and design their own nose cones, or go on and select from a variety of different patterns that are already there. I really like these ones with the sort of girdles that you can that are just ready made to kind of slide onto the container, because it's a little easier for students to attach them. You don't need hot glue or any of those other things. I think Kelsey was going to show you one of the 3D printed nose cones we had teachers create last summer for some chemical rockets, and which we'll talk about those rockets in a little bit. But those are designs that teachers actually made based on studying the measurements of the rockets. So this is bringing that engineering design in really hard to combine with that forces in motion. So we're talking about stability here, and what creating stability and balance does for an object in motion. And it can be really fun. The time is really what you kind of have to worry about here, right? 3D printers are not the fastest things. So I would definitely say that if you're planning on doing this with a large number of students, either to put students in groups or to prepare yourself way ahead of time, because it's going to take a hot second to print these out. Awesome. So I'm looking at some of the things coming through the chat. As well. Michael, I totally hear you. And that's why I put that caveat on there, because I can hear Michael, another Michael, my first boss, in my ear saying that's why we use gimbaled engines in space. So picky but correct. Absolutely right. We use the fins to control them in the atmosphere. And then we have to use other types of rockets, those like smaller rockets or engines that can move once you get into space. Excellent point. Well taken.
Well, that's a great extension for students as well, right? So talking about the effects of air resistance that we have in our atmosphere versus, if you've ever seen the relaunch of the Apollo. So once the lunar lander comes down and then they separate from the lunar lander to go back up and meet with the command module. And it's such a simple reaction compared to what happened for it to get off of Earth's surface, right? And you could show that to students and really get them to ask those questions. Well, why? Why is this a very different chemical reaction? Or, we don't need all the fuel, we don't need all the fire to be happening. We just need a little bit of that force connecting to force in motion to get it moving in that direction.
Yeah, totally. And one cool thing on the How Things Fly website, it talks a lot about the differences in the forces of flight between in Earth's atmosphere and in space, and the different forces of flight that work in space. It trips students up a lot when you tell them that there's gravity in space. And that's a great conversation that you have about what what microgravity means and what that weightless state is. So lots of cross science connections there. So I'm going to motor a little bit just so we have plenty of time for questions at the end. But talking about model rocketry here, you can use model rockets from a variety of different places. We tend to use Estes rockets in a lot of our programs because they come in kits that are really easy to put together in some cases. The great thing about Estes is that they help you select them, right? There's like beginner, intermediate, advanced, and super duper expert rockets that you can kind of pick and choose from. And I put $0 on here because there's often a lot of ways to get model rocket kits at almost no cost. The photo in the top of that slide is actually from Civil Air Patrol, which is an organization that promotes aviation to students, but also they support teachers. I know a lot of teachers that I know have use Civil Air Patrol to take discovery flights, but they also have STEM kits, and you can often get rockets from them for free in STEM kits. So if you wanted to kind of dip your toes into model rocketry, you can do that as well. And these are actual chemical rockets, so they have engines and require igniters, which you can purchase. Estes is also really great because they've got lots of really detailed safety instructions and videos. So I launched a chemical rocket for the first time last summer and felt really good about doing it with a bunch of middle school students because we're really well prepared for it. And then kind of leveling up with those, Estes actually makes, and you could make yourself or buy from a variety of places, rockets with a payload in there. So shout out to Kate in this photo, who is Kelsey's predecessor. She was our last fellow. This is part of her tutorial that she did on how to put together these green egg rockets. And they're actually rockets that are made to loft an actual egg. So if you have any leftover Easter eggs around, that could be a great one to use those up. But we actually used a sensor called Pocket Lab to put inside of our rockets. And there's a variety of different sensors you can use to put inside of these rockets. But we use Pocket Lab to measure altitude, acceleration, and get a little bit of data back. We lost a couple of Pocket Labs, I won't lie, in the in the process of doing this. But it was really fun to kind of level up that a little bit instead of just kind of lofting an egg and thinking about, how you might protect that egg when it's coming back down to Earth. We gathered a lot of data on that rocket launch. And this was the rocket launch that we had teachers create fins and nose cones for their rockets too. So we really got to tailor the experience. This is probably the highest prep, highest cost if you're looking at a sensor like Pocket Lab. And also purchasing kits like those green egg kits. I'm going to let Kelsey chat about Pocket Lab in just a couple of minutes. There's a couple of different sensors that we use to kind of explore this with students as well. But like I said, another key concept here being safety. You'll see in the bottom of that image there, the kind of suggested distance or suggested field you need to launch these rockets based on what size engine you use. Tons of different feedback on this. We're happy to talk more about it. And also in our learning lab, we've got lots and lots of links to different projects and ideas and things that you can do with rockets like this too. So I'm going to turn it back over to Kelsey to talk just briefly about her flight and rocketry unit that she does with her students before we open it up for questions.
Thanks, Shannon. So I do a unit of flight and rocketry. So it's really starting with air resistance and talking about the properties of air that even make it possible for all of these pieces to happen. So starting with parachutes and having students build parachutes to try to float an egg, or I try to use something reusable. Like I will take the plastic eggs and fill them with different weights. So students can start with a pretty low weight and then use that. And if they're fairly successful, I let them move up to the next weight. And with this one, I have a picture here of my model parachute. But after showing students my model parachute and having them build one based on the model, this is a really great opportunity to let students explore and say, okay, well, what could work better? Like if I could create a different design, how could that create more air resistance? Because really with parachutes, you want that air resistance to slow the thing down. So starting with parachutes and then talking about properties of gases and air with hot air balloons. So we go from parachutes to designing their own hot air balloons and getting those to what's the best shape? Does shape matter? Does the size of the little spot where the hot air is going up, does that matter? So they're investigating those pieces. And then we get into flight. And flight is really where I start to bring in that How Things Fly website, starting with Bernoulli's principle, because students need to understand Bernoulli's principle before they can really understand how it is that we get airplanes up in the air. And so going through all of that, so another thing I want to talk about with flight is I do a paper airplane design challenge with students, and the How Things Fly website has a wonderful paper airplanes page with lots of different designs. And the wonderful thing about all those different designs and having students build the different designs is you can talk about, again, what's the goal, what's the role of that thing that you're doing. So there are planes that are designed to go really, really fast. And one thing that I like to do is connect the paper airplane design to an actual plane. So if we see that sort of dart, that classic dart paper airplane that's up on this slide, comparing that to something like the SR-71, which was really built to fly really high and really fast. And so it sort of mimics that shape and that design. Versus something like a cargo plane that really needs to just carry a lot of weight and go really far and try not to burn tons and tons of fuel. You can find some really good glider designs that sort of mimic those pieces. So that How Things Fly is wonderful for finding some of those different paper airplane designs. And then after we kind of study our air properties and study our flight and do a little bit more with flight and propellers and things like that, then we get into our rocket design challenge. So again, as Shannon was talking about with the Estes kits, you can really go from, I want something that I can put together with some super glue in less than an hour and go out and fly it. I have a little bit more time in my schedule to for students to use what they call their Alpha 3 rocket, which is a bit more of that intermediate level. And students are having to cut out their fins, sand the fins, glue them onto the tube, which is pretty difficult when you don't. The super glue ones just have a slot that you kind of stick it in, and you can use super glue. If you don't have that, these are just putting that balsa fin, and then they have to really stabilize it, figure out how to stabilize it and glue it on there. In the past, I have had them do where they 3D print their own nose cone, and we talk about things like aerodynamics and why you don't necessarily want a flat head on the top of your rocket and things like that. And then we take them out into a field, and we have one of the best days of 5th grade. It's usually towards the end of the year where they get to launch them over and over again. And so one of the things that it took for me to get really comfortable, like Shannon was talking about, with doing this in the classroom was that safety piece. One of my absolute favorite books is called Make. It's a Make, if you're familiar with that Maker brand, Make Rockets. It's by Mike Westerfield, and I believe we have it linked in one of the resources. But I would sort of find those resources, educate yourself on the safety before you take students into the field to do it. It's not dangerous by any means. I think you just have to know what you're doing, and you have to know how to keep students safe before I would embark on this. But tons of fun. Students are always so excited for this unit, so I would highly recommend diving into it. Try it out yourself. Launch a few rockets first by yourself or with your family and get comfortable with it, and then do it with students. It's great.
And another thing that's really helpful is to potentially, if you're thinking about launching rockets like this, connecting with your local model rocket club. There's many in cities across the United States. You can go to launches and watch them launch rockets. You can often, I know here in Northern Virginia, you can actually take your own rockets and launch them. They've got the appropriate clearances with localities to do it. It's really tough for us because we're very close to an airport. So we have to really think about when and where we launch ours. But that's another way that you could, if you're a little nervous about starting with fuel rockets, you can actually hook up with your local model rocket club too.
Awesome. All right, and then the final thing we're going to talk about real quick is whether you have more time, you've flown rockets and you really want to connect the laws of motion to it, and you want to collect more data and really do some more of those labs in the science classroom. Or if you're like, I don't have time to do the rocket piece, but I'm interested in connecting science with space and rocket launches, Pocket Lab came out with this really great, it's kind of a physics, I would say, a physics data collector. It's on a car, and this is essentially, where'd my little brick go? It's this thing in a car form. And so you can use the GForce. This is called the Pocket Lab GForce. You can use it with the Hot Wheels racetrack. So you can get this fairly cheaply. The GForce, not so cheaply, but you can, once you get them, they're really great, and they're meant to last. These have been dropped multiple times in the course of design and build and trials and tests and collecting data. So they're built to be in classrooms, which is really wonderful. And so what we did is, in concert with some of my TII folks, participants in TII, we got together and we created some useful resources for teachers who want to use the GForce in their classroom to collect data and have students really understand and boil that data down and show and represent and have that claim evidence reasoning on how Newton's laws of motions actually are present. And so they learn about the laws of motion in space. They learn about it, how it connects to things like rocket launches and the DART mission. And then they do the experiment with the GForce to really make those connections. And then you can even collaboratively have them do a design and run experiments to connect that law of motion to a piece. So if they're learning about the DART mission, which I believe is the picture up in the corner, they're designing. You can also do things like open up this top part and add weights to it. So if you're saying that something that's heavier is going to have more force, you can have them test those pieces out, and thinking about that DART mission where we're taking a spacecraft and launching it into a celestial body to see if we can make it move. Then students, after learning about laws of motion, might think, well, I need something that's really heavy because I need it to have more force. So they can design that experiment, run it, collect the data, analyze the data, and then prove to their teacher or to their peers and say, yeah, this actually works out. I guess Newton knew what he was talking about.
Awesome. So we've thrown a lot at folks, and hopefully you found yourself somewhere in that little continuum of high tech, low tech, high prep, low prep. Would love to hear if there's something that you are really excited about exploring. And just to kind of bookend the beginning, we'd love to hear now, on a scale of Redstone to Saturn V, how comfortable you are introducing rocketry. If you're thinking about doing it, would love to hear that 1 to 5 again, or Redstone up to Saturn V if you'd like. And are happy to take questions if folks have them. I see a few people talking about launching Estes rockets and doing paper airplanes at an outdoor event. They're really, really fun. That moment, there's usually a very brief moment when you hit the igniter before the rocket actually goes, and it's a really fun, like heart-pounding moment. And then when the rocket goes, it's super, super, super fun. My at the time 3-year-old helped us launch ours during our TII rocket event. And she still talks about it all the time. Do you remember the time we went to the farm and we pressed the button and the rocket went really high? So it's a really cool thing for students, elementary through high school to do.
For sure, Shannon. I didn't launch my first solid fuel model rocket until I was probably 30 years old, and I even had that like heart pounding, like, oh my gosh, I'm gonna push the button, but it was the coolest thing ever. So you don't have to be a kid to really get into it. It's tons of fun.
Yeah. So Cheryl's talking about really enjoying the straw rockets as an introductory activity. It's great to kind of explore these different pieces here and like go from these smaller activities. These could honestly be used all together if you had the time to do it. Kelsey talked about in her classroom having the opportunity to kind of explore many of these different things that we've talked about today as she works her way up to it. So I see the numbers changing. I see a 2, I see a 4. So like people may be feeling a little bit more confident about using rocketry in the classroom. So are there other questions that folks have? We'd be happy to answer. Kelsey especially can talk about how she's done it with students. We've introduced them with teachers, so please feel free to toss us your questions.
So I think we have a first question here in the chat. The question says, I have done Estes Wizard rockets, say that 5 times fast, but would love a simpler model as parents end up doing so much of the work. You mentioned a rocket that has fins that go in more easily.
Yeah, so I'm not perfectly familiar with what the Wizard rocket is, but they do have, I would just say go to their website, and they've done such a great job of really categorizing their rockets into beginner, so kind of the skill level, the age level, and the amount of time it takes to put it together. So, you might say something might go together really quickly, but you're using super glue. So you're still going to need adults if you're doing that with 5-year-olds, right? To where some of them, I believe you might just have to snap a few pieces together and that would work. But I would just say go to their website and really do a little bit of research, because they do such a great job of breaking that down for people.
Kelsey, did you say it was the Alpha model that you used with your younger students?
Yeah, so I use Alpha, and I believe the Civil Air Patrol uses Alpha 3, which is more of the super glue put together pretty quickly rocket. So even within that Alpha level, there's some different preparation levels. Yeah.
And I'll give you a pro tip, because I learned it the first time I was putting one of the green eggs together. Super glue is what's suggested. But the first time you're putting it together, it's not as easy with students. But using hot glue for me was the way to go. because it dries so much more quickly. There's a potential that the glue will melt when the rocket actually goes, but we actually had a great success with hot glue. So pro tip, try hot glue the first time if super glue is really tripping you up.
Yeah, and it does. It's all based on what your goal is, right? So if you're really into model rocketry and you're saying I want to be a pure model rocket person, somebody's going to say hot glue is too heavy, Shannon. You can't use hot glue, but you know what? We're teachers. We can do we can do whatever we need to do. Though that's one of the things I do like about the rockets that we use in the classroom is you're using wood glue for most of it. Or I like to use Aleene's. If you're familiar with that craft glue, they sell a quick dry option. So it tacks pretty quickly. So students aren't just sitting there holding it for a really long time, trying to wait till it, like an Elmer's glue would be, right? Elmer's glue would take an hour for it to tack into place. Aleene's quick dry is my top tip for for craft glue.
Now, I jumped right into the questions, but first I want to say thank you so much for sharing all of these ideas for, using rocketry in a variety of different ways, different kind of amounts of money that it costs, time, what works for different skill levels. And I've been really excited to see too all the ideas that other people are sharing in the chat, bouncing off of ideas that you've had. Like some of the ones coming in most recently are, thinking about the car that you were showing, Kelsey, also thinking about adding sensors to Pinewood Derby cars too. And so I think there's a lot to be learned from each other in the chat too. There's also an idea about using these as preliminary lessons for drones. So what I really appreciated about what you did too is you talked about ways to involve students in the decision making for how these experiments are going to go. There was one experiment that you talked about specifically where there was an opportunity there to think about the types of things that you want to, or how you want to change the direction of the experiment. And I think that is such a great idea. As we wait for more questions to come in from the audience, I wanted to restate something that I entered in the chat, and Shannon mentioned too that all of the resources that Shannon and Kelsey shared today, we've added links for in the session description. And I think it might be helpful, Shannon, if we take a quick look at the Learning Lab collection and what you've gathered there, just as like an overview of what folks are going to find once they click that link.
So if you take a look at the lab that shout out to my amazing intern Talia put together, you will see our step-by-step walkthrough of the straw rocket activity. That's kind of the most obvious piece there. But then there's also an image of the Artemis 1 launch with some questions there that you could potentially ask students to get their wonderings. It's a great hook and kind of kickoff to see an actual rocket launch. And then as you move through, there are some items from the National Air and Space Museum's collection that we showcase. There's so very many. In the kind of banner image to this webinar, we put the F1 engine from the Saturn V, which is such an exciting artifact to talk about and explore. But there's some artifacts there. And then we provided some links and resources, both to the pieces that we've shared today, that straw rocket activity we shared a little bit of. And then there's also a resources sheet that we put together that connects many of these things to the standards, right? Those force and motion standards. But it has some of the technology we've talked about. It has some lesson plans and activities and some other pieces there. And then you can always visit NASM Learn. So Air and Space has a huge collection of teacher resources on our website if you go to the Learn tab as well. So all of that is in the Learning Lab, and we'll also probably link the archive of this webinar there once that comes up.
That's a lot of really rich and detailed stuff. Thank you too for pulling those together. And thank you to Talia too for building the collection. We still have time for questions. If you have questions about any of the activities we covered, ideas for adapting some of the things they talked about for different grade levels, as we wait for final questions to come in, I just wanted to restate that today's session has been recorded. So if you came in a little bit late or you want to watch something again to get, a reminder of how much time an activity might take, you will be able to do so as soon as the session ends. So if you want to watch the recording at any time, just go back to the spot on YouTube or Facebook where you're watching the session at now. You'll also find a permanent link to this session on the Learning Lab Help Center. Again, the URL is here on the screen. You're going to find a link to this session, other cultivating learning sessions exploring ways to bring museum resources into the classroom, and ways to use the Learning Lab to kind of discover and create with digital museum resources too. So there's going to be a lot on this page for you, including the recording of today's session. Finally, if you are interested in tuning in for another Cultivating Learning session, curious about more ways to use museum resources with students, we've got another session coming up in early May with the Center for Folklife and Cultural Heritage. They're going to be talking about this really cool story map that allows you to explore culture and making across the country. We'll have more details about that session soon. We'll post it on the Learning Lab homepage and on that Help Center too. But for now, if this is something that strikes your fancy, mark down the date and time. It'll be Tuesday, May 2nd from 4 to 5 p.m. Eastern. So it doesn't look like there are any more questions in the chat. Kelsey and Shannon, before we sign off today, is there anything else that you'd like to share?
Oh, great, great question. Sorry, Tess. So just like we said, please feel free to visit Air and Space Learn. We've got lots and lots of resources for teachers there. If you visit the Learn page, we also have all of our upcoming professional development opportunities. We're sort of winding down for the school year, as many of you who are in the classroom, I'm sure, are wishing to start winding down for the school year. Right, this post-spring break point is kind of like the backup hill. But we'll have both virtual and in-person professional development opportunities coming up. Lots of teacher resources to explore. So please feel free to check that out. And also feel free to come and visit the newly renovated Air and Space Museum. We have 8 galleries open at the museum on the National Mall right now. The tickets are free, but you have to get timed entry passes. They're absolutely worth it. The galleries are beautiful. Our colleagues at Air and Space have done an amazing job of redesigning and reimagining the exhibitions, and we hope that folks will come and see these and then the ones that are opening in the next several years as well.
And it's so exciting to hear the museum is back open and ready for visitors. Thank you again, Shannon and Kelsey. This has been a really great session. And for all of you who participated today, whether you were watching or sharing in the chat, it was so great having you with us. Have a good evening.
Thanks, everybody.
Thank you.